Hello guys, so today we'll be doing an example of Euler's method. So let's read the question. Use Euler's method with the given step size to approximate the solution of the initial value problem over the stated interval. And we are given an initial value problem, cosine y, dy dt equals cosine y, and y of 0 equals 1, that's our starting point. And delta t is 0.5, that will be our step size, and our interval is 0 to 2. So let's begin. So let's start with just writing what we know. So we know our differential equation is dy dt equals cosine y. We know our starting point is y of 0 equals 1 or 0, 1. And we know that delta t equals 0.5. That will be our interval. And we're looking for the solution values from 0 to 2. So what is the question actually asking? So it's asking us to approximate the values for the solution from the t values from 0 to 2 with an interval of 0.5. So to approximate these values, you're going to have to use the t value from 0 to 2 using this 0.5 interval. So drawing it out on a number line will help you visualize what we're going to plug into our Euler's method equation. So from 0 to 2, and from a 0.5 interval. So basically you're dividing 0 to 2 by 0.5. So 0.5, go to 1, to 1.5 to 2. Do you see that? So we're increasing each step 0.5. So 0 plus 0.5 is 0.5, 0.5 plus 0.5 is 1, 1 plus 0.5 is 1.5, and 1.5 to 2 is 2. So we got from 0 to 2 using a 0.5 interval. So these are the t values that we'll use, starting with 0.5, and we'll plug it into our Euler's method equation to approximate these values. So we'll be finding a y of 0.5, a y of 1, a y of 1.5, and a y of 2. We'll be finding these. So let's begin. So let's start off by writing our Euler's method equation to use as a reference. So in my last video, I actually used the function notation. Here I'm going to use a more general notation. I'm going to write y sub n plus 1 equals y sub n plus the slope, which is represented by y x sub n y sub n times delta x. So this is the general equation, but instead of x, we'll be using a t because in this case we're in terms of y and t. So now let's just plug in our values. So for our first step, we're going to have to use the initial point to find this y, the y of 0.5. So we're looking for a y of 0.5 that approximates to the y value of the initial point, which is 1, plus the slope of the initial point, and our initial point is 0, 1. So let's find the slope over here. So, or actually, let's do it over here. So dy dt of our initial point, which is 0, 1, equals, so since our dy dt does not have a t value, we won't be plugging in this t because it just requires the y, which is 1, so that'll be cosine of 1. So I'm going to actually plug this in here so I don't have to plug in this big old number separately, so I get it all in one shot on the calculator. So 1 plus cosine 1, which is our slope, cosine of 1 is the slope, and we multiply that by our delta t, which is 0.5. So now let's plug that into the calculator because this we cannot do in our heads. So let's get our calculator out and turn that on. And 1 plus cosine 1 times 0.5 equals 1.27 blah blah blah. And make sure your calculator is in radian mode, not degree mode, otherwise you'll get the wrong values. So let's round that to 1.270. So that's the first approximation. Now we have to do the rest because the problem is asking for all the approximations from 0 to 2. So the next one is y of 1. So we'll just do the same thing as we did for the first step. So y of 1 approximates to the y value of the previous function, which was 1.270, because our point is 1.27. This is our point, so our y value will be that. So we just plug that in here, plus the slope of this point. So our slope will be the derivative function at 1.27, and we're only plugging in the y value because the derivative function only calls for the y value. Cosine of 1.27, right? So we'll just plug that in here and multiply that, kind of run out of space, multiply that by our delta t, which is 0.5, and we do that on the calculator. Yeah. 1.27 plus cosine 1.27 times 0.5, which is 1.418. I will round that. 1.418. So that is our approximation for y of 1, and our point is 1.418. Now the next step. So what is our next t value that will go into this y? Yep, it will be 1 plus the interval 0.5, so it'll be 1.5. So 1 of 1.5 approximates to the y value of the previous, okay, you can't see that, the y value of the previous one, which is 1.418, plus the slope of this point, of the previous point, which is dy dt of this point. And we won't be using the t value because our derivative only calls for cosine of y, not cosine of t or anything. So just cosine of the y value. Cosine of the y value. So we plug that into our equation, and we multiply that by our delta t, which is 0.5, and now we plug it into the calculator. 1.418 plus cosine 1.418 times 0.5, and that equals 1.494. So our approximation for y of 1.5 is 1.494, and our point is 1.5, 1.494. That's our point. So now our last step is to find the y of 2, which is our last point. So let's approximate y of 2. So y of 2 approximates to the y value of the previous, which is 1.494, plus the slope of the previous point, which is 1.494. So the slope will be dy dt. Again, Euler's method can be really repetitive, and that is the point. 1.5494, and we won't be using the t value again because cosine, the derivative does not call for the t value. So cosine of 1.494, I'm kind of running out of room, but it is fine. So we plug that in, we plug our slope in, which is cosine of 1.494 times our delta t, which is 0.5. Plug it into the calculator again, 1.494 plus cosine 1.494 times 0.5, which is, oh, I added something. Oops. 1.532. So 1.532 approximates to that. So those are our approximations. So most of the time for these questions, they'll ask for you to show your answers in a table format or a graphing format or a graph. So I'll just show you how we will do that, because this question does not want a single approximation. It wants all of the approximations for each step. So to do that, we'll have this little graph right here, and for our first row, it'll be labeled n. So what is n? N is actually quite simple. It's just the interval. So for this case, we went from 0 to 2, and each step was is represented by n. So this one, which goes with all the first like y1 and t sub 1, this goes with n sub 1 and respectively n sub 2, n sub 3, n sub 4, because we have 4 steps, right? So n is just the steps, like the number of steps that you have. So n, we have 1, 2, 3, 4 steps, because we went from 0 to 2 with an interval of 0.5, which is 4 steps. So then now you just write in your t sub n and your y sub n, which correspond with the following steps. So for our first t sub n, which is just, what was it, 0.5, and the next one is 1, and the next one is 1.5, and the next one for 4 is 2, because each step is going up 0.5, and we start at 0.5 because it's our first. And for our y values, this is just all the work that we did to get our approximations. These are just the approximations. So for 1, what was that? I believe it was 1.27. For our n's, for our second one, it was 1.418. And for 1.5, it was 1.494. And for y of 2, it is 1.532. 532, sorry. So that's just the table for it. And from the table, you can make your graph. So you just graph it out. Let's use a different color. Let's use purple. So now you just graph it out from this table, and you'll get this, like a simple graph. Doesn't have to be anything special. And then we have, so this will be your t's, this will be your y's, just like normal, like usual. 0 to 2, 1, 2, and then here we could just go by 2 again. So, and this could be 1.5, so we can have an easier way of plotting these points. 1.5. So our first one, this is our t's. Actually, I should label that t and y. Okay, Let's zoom into that so we can see it. Okay, so now let's plot in our points. So for 0.5, our y is 1.27, so that will go like right here. And for 1, our y is 1.418, so that'll go just beneath the 1.5. And 1.5, our y value is 1.494, that'll just go, oops, sorry. That'll go just right above the other one, beneath the 1.5 though, and for 2, our y value is 1.532, so I'll just go just slightly above this in that general area. It doesn't have to be perfect, but this is just the general picture of the graph that you will have when you're writing out your solutions. So yeah, that was finding approximations using Euler's method. Thanks for watching, and comment, like and subscribe, and I hope you learned a lot. Thanks.